Episode 6. Title of the course: Advanced Material Science, Unit 2. In this unit, we will discuss about structural features and mechanisms of polymers. A polymer is a very large molecule comprising hundreds or thousands of atoms formed by successive linking of one or two, occasionally more types of small molecules into chain or network structure. The concept of polymer is one of the greatest ideas of 20th century. It emerged in the year 1920s. The influence of polymer concept spread rapidly into many areas of natural science and technology. Within the life science, it fostered the emergence of molecular biology through the study of natural macromolecular substances such as proteins, nucleic acid, and etc. Of the polymer materials in engineering use, the plastic form of the largest group by production volume. It is common to subdivide plastics in thermoplastic and thermosetes or thermosetting resin. The thermoplastic comprise the four most important commodity material: polyethylene, polypropylene, polystyrene, and polyvinyl chloride, together with a number of more specialized engineering polymers. The term thermoplastic indicates that these materials melt on heating and may be processed by a variety of molding and various techniques. Important thermosets include alkyds, amino and phenolic resin, unsaturated polyesters, and polyurethanes, substances which cannot be melted and remelted but which stand reversibly. The distinction is important in that production processing, the fabrication techniques for thermoplastic and thermosets differs. Examples for plastic, that means thermoplastics: polyethylene, it is called as PE; polypropylene, it is called as PP; polystyrene, it is called as PS; polyvinyl chloride, PVC, it is well known compound; polyacetyl, POM; acrylic, PMMA; polyamide, it is also well known as nylon, PA; polycarbonate, PC; polytetrafluoroethylene, PTFE. Next, we will discuss about plastics, in particular thermosets: epoxy, EP; melamine, that means formaldehyde, MF; ureformaldehyde, UF; unsaturated polyester, UP; phenolic, PF; polyurethane, PUR. Next, we will see elastomers, natural rubber, NR; butyl rubber, IIR; polychloroprene, CR; synthetic polyisoprene, IR; nitrile, NBR; silicon rubber. These are the main components of elastomers. In the year 1870, in USA, cellulose nitrate was first beginning of commercial production. In the year 1905, Germany beginning of commercial production of cellulose acetate. In the year 1913, Germany beginning of commercial production for polystyrene. In the year 1934, UK beginning of commercial production for polymethyl, PMMA. In the year 1933, Germany and USA beginning of commercial production for polyvinyl chloride, PVC. In the structural aspects, first we will discuss macromolecules and polymers. Macromolecules, that means big molecules, are molecules with large or very large molecular mass. Molecules of common low molecular weight substance such as water, that means H2O, oxygen, O2, carbon dioxide, CO2, toluene, C6H5, CH3, etc. have relative molecular mass of the order magnitude of tens or hundreds. Macromolecules have masses hundreds up to million times larger. High molecular mass and corresponding structure of macromoleculars are causes of their specific property. For instance, a molecule of polyethylene, one of the most common synthetic plastics, a small section of which is described by the structural formula, comprise thousands up to hundreds of thousands of carbon atoms, and its relative molecular mass can be range from tens of thousands to million. A polymer is material which is composed macromolecules of the same kind. Polyethylene consists of large number of polyethylene molecules. A material is classified as polymer if an addition or subtraction of a few basic structural units to or from its macromolecules. That means in the case of polyethylene, of a few CH2 units does not change its property. Substance composed of molecules containing a few up to tens of basic structural units, that means CH2 groups in polyethylene, are called oligomers. Oligomers are a transition between lower molecular weight substance and polymers. A change in the number of basic structural units in oligomers molecules results in an observable change of some properties of the substance. According to their origin, polymers are divided into two basic groups: natural polymers and synthetic polymers. The most important classes of natural polymers are basic structural material of plants, proteins, fundamental structural materials of animals, and nucleic acids, carries the genetic information. Synthetic polymers are modern material surroundings us in everyday life, as construction, insulation or packing materials, synthetic fibers, coatings, etc. The reaction by which all synthetic polymers and many natural polymers are formed from lower molecular weight substance are controlled by laws of statics, and the resulting polymer comprise macromolecules with different molecular masses. The relative amount of molecules with specific value or molecular masses in a polymer is described by distribution function of relative molecular mass. The distribution function affects significantly many properties of polymers and is one of their important characteristics. Then we move on to synthesis of polymers and its structures. The mechanism of synthesis of natural polymers in living organisms, the biosynthesis, is extremely complex and is one of the most important topics in biochemistry. The chemistry of formation macromolecules can more easily be described with synthetic polymers. Low molecular weight substance used for synthesis of polymers are called monomers because of their specific structure and reactivity. Monomers can undergo a reaction called polymerization, which convert monomers to macromolecular substance, that is polymers. As example, two basic and relative simple types of polymerization reaction will be described, namely radically polymerization and polycondensation. The ability of monomers to polymerize radically is most frequently conditioned by the presence of double bond between two adjacent carbon atoms in the molecules. Each of the two double bonds is formed by two electrons shared by both carbon atoms through the action of substance called initiator. One of the bonds disconnects in the such way that one of its electron form a bond with initiator molecule and the second electron remains free, unpaired for a short period of time. The structure of unpaired electrons are called free radicals or just radicals, and hence the term radical polymerization, the radical resulting from the reaction of an initiator molecule with a monomer molecule, has the potential to disconnect one of the two bonds of the double bond of another monomer molecule, and so to attach to the other molecule, giving to join monomers units with a free radical. This addition reaction repeats several hundred up to several thousand times, and in this way a polymer molecule builds up. As an illustration, the structures of three simple but industrial extremely important monomers and polymers form from them: ethylene, polyethylene, vinyl chloride, polyvinyl chloride structures. The name vinyl chloride derives from the combination of the name of vinyl group CH double bond CH2 and the name of the salt with chloride anions, chloride. That name is not quite rigorous because the bond between vinyl and chlorine is a covalent, not ionic bond, which means that vinyl chloride is not a salt. A molecule of styrene consists of vinyl group bond CH double bond CH2 and benzene ring, that means bond C6H5. Thus, an alternate name of the styrene could be vinyl benzene. As far as the volume of production is concerned, the above three polymers are basic products of huge industries of synthetic polymers, the world production of which amount of 2/10 of million of metric tons. Condensation in organic chemistry means reaction in which two molecules join, giving rise to a larger molecule while a small molecule, a molecule of water, is eliminated. For instance, a carbolic acid, the characteristic group of which is COOH, that means acid group, reacts with an alcohol, the characteristic group of alcohol being OH, with the elimination of molecule of water to form a molecular ester. Acetic acid plus ethyl alcohol gives ethyl acetate. The byproduct is water. This reaction is condensation of acetic acid with ethyl alcohol. To utilize the principle of condensation for synthesis of macromolecules, we must start with monomers or more than one type of monomers, the molecules of which have two or more functional groups capable of condensation. For example, suitable monomers for polycondensation are hydroxy acids with the general formula HO or COOH, each molecule of which contains both one carboxylic acid and one hydroxy group. By a multiplicity of condensation steps, that means by a polycondensation reaction, a polyester macromolecule form. The structure of the polyester macromolecule is R single bond COO single bond R single bond COO single bond R single bond COO R bond. Formula of a section of polyester molecule formed by polycondensation. An alternative way to synthesis polyester is to start from two monomers, a bicarboxylic acid general formula HOOCR1 COOH and dialcohol, that means diol general formula HOR2OH. The reaction of these two monomers yields a polyester with a somewhat different structure, that is R1 single bond CO single bond OR2O single bond OCR1 CO single bond OR2O single bond OCR1 CO. This is the formula of the section of polyester molecule formed by polycondensation of a dicarboxylic acid and dialcohol. In addition to radical polymerization and polycondensation, there exists a large number of other important mechanisms of polymerization. Also, the number of monomers and corresponding polymers is extremely large. In fact, it's unlimited. Out of the vast amount of polymers described in literature, only a minute fraction are produced in industry. If more than one monomer is used polymerization reaction, the process is called copolymerization and the resulting polymerization is copolymer. Using various combination of monomers and varying their ratios in the copolymerization, a literally infinite number of copolymers can be prepared. The sequential distribution of the monomeric unit in the copolymerization molecule play the major role in determining the property of copolymer. The most important type of copolymers are statistically copolymers and black copolymers. In a binary statistical copolymers of monomers A and B, the sequential order of a monomeric units is controlled by some type of statistics, and structure of a segment of a copolymer molecule can be represented schematically as A, B, A, B, 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 A, B, B, A, B, B. In a black copolymer, identical monomeric units form long sequence. This is A bond, A double bond, A B double bond, B B double bond, B A double bond, A double bond A would be a schematic representation of a tri-block copolymers. Next, we will discuss about structure of macromolecules. By the reaction described, essentially linear chain-like macromolecules are formed. Parts of a molecule adjacent to a single bond rotated about this bond. In a typical macromolecule, there are large number of single most C bonds and isolated macromolecule. Example, in highly dilute solution, assume due to the fast rotating of its parts about all single bond in the time of a large, virtually infinite number of conformation from coil to extent 1. By far the most frequent conformations are those called statistical or random coil. In the random occupied by macromolecule with random coil conformation, the segment of the macromolecule occupies just a small volume fraction of the volume of the domain, typically a few % or even less, most of the space being occupied by solvent molecule or segment of the macromolecule. The concept of statistical coil is of the prime importance for the understanding of relation between structure and properties of polymers. If some of or all monomer molecule in a polymerizing system have two double bonds or more than two groups capable of undergoing polycondensation reaction, the resulting macromolecules are not linear but branched. For instance, when a monomer molecule with the functional group capable of condensation is incorporated in a macromolecule, it can become trifunctional branch point because three chains can engage from it. Similarly, a monomer molecule containing two double bonds or four functional groups capable of condensation can give rise a tetrafunctional branch point in a forming macromolecule because four chain can meet at this point. Branch point can also be generated in exciting macromolecule by irradiation, heat treatment, aging and some other process. There are several types of reaction that result in branched macromolecules with trifunction branch point in which the macromolecule side chain are attached to the main chain. The backbone macromolecule of this type are called graph macromolecules. The next topic is Thermoplastic. First of all, I will introduce about thermoplastic polymide. Novel thermoplastic polymide TPI offer several potential advantages over thermoset polymides. First, TPI has an identified shelf life, low moisture absorption, excellent thermal stability and chemical resistance, high toughness and damage tolerance, short and simple processing cycle, and potential for significant reduction in manufacturing costs. Second, they have the ability to be remelt and reprocessed, thus the damaged structures can be repaired by the applying heat and pressure. Thirdly, TPI offer advantage in the environment concerns. Usually TPI has very low toxicity since it is the completely imidized polymer, does not contain any reactive chemicals. Due to their remelt possibility by heating and redissolvability in solvents, TPI could be recycled or combined with other recycled material in the market to make new products. TPI with controlled molecular weights was prepared by the reaction of ODPA with 6-FAPB in the presence of PA as end-capping agent in NMP at elevated temperatures. Next, thermoplastics and thermoplastic resins. Thermoplastics and thermoplastics resins are raw unshaped polymers that turn to liquid when heated and turn solid when cooled. They can be rapidly remelted and remolded, allowing parts and scraps to be reprocessed. In most of the cases, they are also very recyclable. Types of thermoplastic resin. Thermoplastics are based upon a variety of chemical systems listed in the global market. The most important one of include polyvinyl chloride, polypropylene, polycarbonate, ethylene copolymer and ABS. First one is polyvinyl chloride is thermoplastic polymer widely used in construction because it is cheap, durable and easy to assemble. It can be made softer and more flexible by the addition of plasticizer. It is a controversial material because of toxins in it may layerable during its production and lifetime. Polypropylene is the thermoplastic polymer that is used in packaging, textiles, stationery, laboratory equipment and plastic parts. It is unusual resistance to many chemical solvents, acids and bases. Next one is polycarbonate is a thermoplastic polymer used in electronics, construction, data storage, automotive, aircraft and security application. It is very durable, transparent material with a high impact resistance but a low resistance. Ethylene copolymers. The ethylene copolymers are polymers that have ethylene as one of its monomer bases. They are used in packaging, sporting goods, shoe and superplasticizers in cement production to improve flow characteristics. ABS are a hard rigid thermoplastic polymer. It provides good chemical and creep resistance along with dimensional stability. ABS is used in many industrial applications and in wide array of applications. It is generally expansive but prone to crack under stress. Choosing a filler material. Some thermoplastic containing filler materials such as powders of fibers to provide improved strength and stiffness. Fibers can be either chalk or wood and commonly include glass, fiberglass or cloth. Some products contains lubricant fillers such as graphite or molybdenum disulfide. Other containing fibers, metal powders or inorganic fillers with ceramics and silicates. Advantages of thermoplastic composites. There are two major advantages of thermoplastic composites. The first is that many thermoplastic resins have increased impact resistance to comparable thermoset composites. In some instances, the difference is as high as 10 times that impact resistance. The other major advantage thermoplastic composites is the ability to reform raw thermoplastic composites at room temperature or in the solid state. This allows thermoplastic composites to be reformed and reshaped. For example, thermoplastic composites rod could be heated and remolded to have curvature. This is not possible with thermosetting resin. This is also allows for the recycling of the thermoplastic composites at end of the life. That means in theory not yet commercial. Disadvantages of thermoplastic resin. Because of thermoplastic resins is naturally in a solid state, it is much more difficult to fiber. The resin must be heated to the melting point and pressure is required to fiber, and the composite must be cooled under this pressure. This is complex and far different from traditional thermoset composite manufacturing. Special tooling, technique and equipment must be used, many of which is expensive. This is the major disadvantage thermoplastic composites. Advances in thermoset and thermoplastic technology are happening constantly. There is place and use for both, and the future composite does not favor one over the other. Thermoplastic are defined as polymers that can be melted and recast almost identically. They are molten when heated and harden upon cooling. When frozen, however, the thermoplastic becomes glass-like and subject to fracture. These characteristics which the material its name are reversible, so the material can be reheated, reshaped and repeatedly changing. As a result, thermoplastic are mechanically recyclable. Some of the most common type of thermoplastic are uses in many ways. Properties of thermoplastics. Thermoplastics have simple molecular structure compressing chemical independent macromolecules. Upon heating, they are softened or melted, then shaped, formed, welded or solidified. When cooled, multiple cycles of heating and cooling can be repeated, allowing reprocessing and recycling. Applications of thermoplastics. Thermoplastics have been around for a long time and are an important component of everyday life today. For example, ABS is a thermoplastic used for manufacture sports equipments and sports goods, and also making of toys. The major use of ABS is various of automobile parts. Next one is polycarbonate is used to make CDs and DVDs, and also used to make drinking bottles. Polycarbonate is majorly used in the field of food storage containers. The polycarbonate is also used to make eyeglass lenses. Next one is polyethylene is probably the most common thermoplastic and is used to make shampoo bottles and plastic grocery bags. The most important application of polyethylene is probably the most common thermoplastic, and it is used to make bulletproof windows, glasses, bulletproof cars, bulletproof rooms and etc. Dear students, in this episode we discussed about structural features and mechanism of polymers and also discussed thermoplastics. Thank you. We will discuss another topic in Unit 2 in the next episode.